All right, so today in physics, we are going to be looking at units, scientific notation, and significant digits. So hopefully after this lesson, you will understand units, scientific notation, and significant digits. For units, you've dealt with most of the units in other science classes. Scientific notation, if you've had me for math, you've dealt with scientific notation. If you've taken a science class, usually Chemistry 1 talks about scientific notation, and it also talks about significant digits. So hopefully you're familiar with most of the stuff that we're going to go over today. Almost every other country in the world except for the United States uses a system of units called the SI, most often just referred to as the metric system. I'm sure you are aware of that. The mass majority of the world does not use feet. They use meters or kilometers instead of miles. So in the SI system, in the metric system, the meter is the base unit for length, and it's approximately 39.37 inches. If you've seen a yardstick, a meter stick is just a little bit longer than that. A kilogram is the base unit for mass. So instead of weighing in pounds, we're going to be weighing in kilograms. And then the second is the base unit of time. Coulomb is the base unit for charge, and you may or may not have heard of that one before, Coulomb. We will deal with that later, but when we get to charge, that is the base unit, Coulomb. Most units are called derived units because they are defined by some combination of other base units. So a meter per second would be an example, or feet per second, miles per hour. Those are derived units because those are combined with other units. So Newton is the most commonly used derived unit that we're going to use in physics, and it is a kilogram meter per second squared. So kilogram meter So kilogram times meter per second squared. That is a Newton. And we'll discuss more about Newtons in later lessons. And the book says, for now, we will content ourselves with the knowledge that this book weighs about 20 Newtons, and an apple weighs about 2 Newtons. So if you want to pick up your physics book, that's about 20 Newtons, whereas an apple is about 2 Newtons. All versions of metric units are related to the base unit by multiples of 10 or 1/10. So whereas we have 1 foot is 12 inches, and then 1 yard is 3 feet, and a mile is 5,280 feet, they aren't strange numbers like that. 1 centimeter or 100 centimeters is 1 meter, or 1,000 meters is 1 kilometer. They're differing by base unit 10 to a power. So deca is going to be a prefix you'll see. It means 10. A decagon you dealt with in geometry, hopefully. That was a 10-sided figure. A hecto means 100. Kilo, a kilogram, means 1,000. Deci means a tenth. Centi means 100th. And milli means 1,000. So if you think about a century is 100, and a millennium is 1,000, where the 100 and the thousands kind of come from. This list gives you some examples of the prefixes that we'll use. It's also in the book on page 1. Looking at scientific notation. When you write a number in scientific notation, you're going to have 2 factors. One is going to be a decimal number with the decimal point immediately following the first digit. And then the other one is a power of 10 that tells the true location of the decimal point in the number. So 4.2 times 10 to the 6th would be in scientific notation. You have a decimal number where the digit is immediately following that very first digit. And then we have times 10 to some number that tells us where the decimal point actually should be located. Okay? The positive exponents are going to indicate that the decimal point is to the right of where it is written. So when I said 4.2 times 10 to the 6th, you're going to do 4.2, and then you're going to move the decimal place 6 times to the right. So 4.2 times 10 to the 6 is really 4,200,000. And if you have a negative exponent, it means that the decimal is to the left of where it was written. So if I had 4.2 times 10 to the negative 2, that would be, you would write your 4.2, and then you're going to go to the left 2 places. So it'd be 0.042. Okay, so we're going to put these in standard form. So the difference between standard form is that you're going to put it without the times 10 to the whatever. So right now they are in scientific notation, and we want to put it in standard form. So if it's a negative number, which direction are we going to move it? To the left. So we have 4.16. And then you got to move it to the left 13 times. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Kind of ran out of room there. So we're going to have 0.00000000000, and another 0. Should have 12 zeros and then 416. So that would be putting it in standard form. Obviously, this is a lot more cumbersome to have to write because you have to make sure you have the right amount of zeros, whereas this number is much more compact. So that's why scientific notation is going to be the preferred method. So throughout the year, whenever you're writing your answer, if it's 20,000, then you can write 20,000. But if it has a lot of zeros, especially if it's a negative number, point something, they're frequently going to put it in scientific notation. So that's pretty much going to be the standard. Although you don't have to. For most of them, they are going to put them in scientific notation instead of standard form. So for this one, we're going to move it to the right because it's a positive number. And we're going to go 5 places. So 1, 2, 3, 4, 5. So we need to add 3 zeros. So you have 416,000 for your answer. Now for this one, we want to write the numbers in scientific notation. So we need to count how many places we have to move the decimal place. So for this first one, we have to move the decimal place so that it is behind the very first number digit that we have besides 0. So we're going to move it 1, 2, 3, 4, 5 places. So that's going to give us 3.2 and then times 10. Now is it going to be a positive 5 or a negative 5? Hopefully you just said a negative 5. And it is a negative because that's a really, really small number that we're starting with. Anytime you have a small number, that means negative. Okay? So for this next one, it's a big number. So that means that our exponent is going to be a positive. So we need to move it 1, 2, 3, 4, 5, and we've got to move it one more time so that we only have one number to the left of it. So that's a total of 6. So 7.15 and you don't have to write all your zeros, times 10 to the positive 6. You only need to write your digits 1 through 9 when you put it in scientific notation. However, if there had been a 1 here, we would have to write those 3 digits. Okay, looking at this one, we need to put it in scientific notation. So again, we're going to move 1, 2, 3 places. So we're going to have 4 times 10. Now we moved it 3, so that's a plus 3, but the exponent was already a negative 10. So negative 10 plus 3 is going to become a negative 7. And so that would be your answer. For the last one, y'all pause the video real quick and see if you can do it by yourself. All right, so for this one, you're going to move it 3 places, 1, 2, 3. And so we're going to have 7.642 times 10. We moved it a positive 3, and there's a 5 already there, so that's going to become an 8. So there is your answer. Okay, so now we're going to look at another example where we're going to add these numbers. So the problem with trying to add in scientific notation is that these numbers right now aren't currently in the right form. And so that's because this is to the 3 and this is to the 5. And so we can't just add them together because the exponents aren't the same. So we need to put them so that they are in the same, where the exponents are the exact same. So you can either make them both a 3 or both a 5. So it doesn't really matter. I'm going to change this first one so that it's a 5. So 4.0, to make it into a 5, I'm going to need to move it 2 more places to the left. So there's 1 and there's 2. So this number is going to become 0.04 times 10 to the 5th. And then this top number is 3.0 times 10 to the 5th. And so now that the exponents are the same, we can add them together. So we get 3.04 times 10 to the 5th for your answer. Now let's say that we wanted to move it so that the second one is in 10 to the 3rd instead of changing the first one. So if we're going to change 3.0, we would need to make it 2 places to the right. And so we would have 300 point whatever times 10 to the 3rd, and then 4.0 times 10 to the 3rd. And so when you add those, you get 304 times 10 to the 3rd, which isn't in scientific notation. We have to move it 2 places to the left. So 3.04 times 10 to the 5th. You get the same answer that way. You can also change both of them into standard form. So 4 times 10 to the 3rd would be 400, and 3 times 10 to the 5th would be 3, 1, 2, 3, 4, 5. And then you get 304 and 3 zeros, 304,000. And if you put that in scientific notation, you get back with what we started with. So any of those work. You'll figure out as you do them which one is the quickest or which one you prefer. It doesn't matter to me, whatever you would like. Okay, so now we're going to simplify these. When we are multiplying and dividing, we do not have to change them so that they have the same powers. We can multiply, and when we multiply, you add your exponents. So what I like to do is get one number in the numerator and one number in the denominator. So to do that, we're going to say 6 times 3, which is 18, and then times 10. 5 plus a negative 3 is a 2. And then we have over 2 times 10 to the 4th. So that's the first thing that I like to do. After that, you want to divide. So 18 divided by 2 is 9. And then our exponents here, when you divide, you have to subtract. So 2 minus 14 is negative 12. And so that would be your answer. Okay, so that's all you have to do with those. If you have taken Saxon math, you have done these before. They were preparing you to be able to do these types of problems, and you didn't even realize it. Okay, so now we're going to look at this one. The first thing that you want to do is to put all of your numbers in scientific notation. That'll make it a lot easier to work with. So for the first number, you can make it 1.6 or you can make it 16. I did just say put them in scientific notation, but if you want to make them all whole numbers, that is okay to do. So I actually am going to make it 16 instead of 1.6. So I'm going to move it 5 places. So I'm going to have 16 times 10. So it was negative 7, and then I added 5, or I subtracted 5 more. So negative 7 minus 5 is going to be negative 12. Now for the 5,000 is going to become 5 times 10 to the third. And then you're going to have 4 times 10 to the negative fourth. From there, you're going to do the denominator, same way. 2 times 10. We moved it 3 places, so that's going to become a positive 7. And then 1 times 10 to the negative 4. And then again, just like on the last one, we want to get one number in the numerator and one number in the denominator. So we're going to do 16 times 5 times 4. And that'll give you 320 times 10. And we have negative 12 plus 3 minus 4. So that'll give you negative 13 over 2 times 10 to the third. From there, you're going to divide 320 by 2, and that'll give you 160 times 10, and we're going to subtract. So we're going to do negative 13 minus 3, which is negative 16. And then the last step is to put it into scientific notation. So 1, 2. So we have 1.6 times 10 to the negative 14. And so that would be your answer. So hopefully you've dealt with scientific notation before. You definitely want to be able to put numbers into scientific notation because you're going to have to do it all throughout the year. All right, so now we're going to look at significant digits. If you've taken chemistry 1 or 2, you should be familiar with sig figs, hopefully, significant figures. So when we use measurements in our calculations, we have to be very careful not to assume that the answer we get is more precise than what is warranted by the preciseness of the measures that we use to make our calculations. So you just have to be really, really careful about your significant figures in your final answer. So I want you to pause the video and y'all read pages 4 and 5 in your textbook about significant digits. It starts about halfway down on page 4. It says 1.C, significant digits. And then you want to read all the way down the page on page 5 about significant digits. Hopefully it's a little bit familiar for you, but once y'all are finished, y'all can stop. After y'all have all finished reading, y'all can stop and discuss it amongst yourselves, and then y'all play the video and we'll keep going. All right, so after y'all have discussed it, we're going to look at our rules for our significant digits. All non-zero digits are significant, so that would be 1 through 9. Every 1 through 9 is a significant figure. All interior zeros, the zeros that are between non-zero digits, are significant. So if you have 1, 0, 0, 1, that is, these two zeros are significant because they are in between non-zero numbers. Okay? Trailing zeros after the decimal point are significant. So what that means, if we have 0.4, there is no need to write those 3 zeros. So what that means is these numbers have to be significant. Otherwise, you wouldn't have to write them. So since they're written, that means that they are important. And then if the absolute value of a measurement is greater than 0, but less than 1, the zeros that are immediately to the right of the decimal point are not significant. So if you have 0.0004, these numbers are not significant. You do not have to include those in your sig figs. Okay? So those are your rules for significant digits. And over the next couple of lessons, your homework will ask you to practice stating the number of sig figs in each measurement so that you can get familiar with those rules. Because eventually, you're going to have your sig figs right to be able to get the answer correct on your test. Okay, so in this book, they also use a precision bar to indicate the precision of a whole number measurement with terminal zeros. So if the precision bar is not used, then the number is just an estimation, it's approximate, and none of those zeros are significant. So if you have 40,000, you only have one sig fig, this 4 right here. If you have 40,000, you have 2 sig figs because that precision bar tells you that 0 is significant. If you have 40,000 with a bar here, that means that all of them are significant because it's telling you it's precise to that number. So that's what the precision bar looks like. So hopefully that helps you a little bit with your sig figs. So sig figs only matter for your final answer. When you're working through things, do not use them in your computations. Use the entire number in your work and apply your sig figs only at the end. It's going to take some getting used to. If you've had me before, then I've been trying to get you used to that. Use the whole number that your calculator gives you. Now, when you're writing out your work, you don't have to write the whole number in the calculator. You can just round it to whatever you want. That's just for your use, for you to have written down so you can kind of see what you're doing. But whenever you are working through things, don't round anything. You've got to use the whole decimal. And if you don't, right now it may not affect it, but maybe once or twice. But as we go through it, it'll start affecting your answers, and you'll end up getting the problem wrong. And it's not because you don't know how to do it. It's only because you didn't do your sig figs correctly. So do not worry about sig figs until you get to the very final answer. Okay? Your homework tonight is 1 through 20. So make sure that y'all work through those, and then y'all can go over any questions that you have tomorrow.